when we go for a large particle, something like this, so then what happens is that this gas molecules which enters into the system has to go through these bigger particles, which offers a lot of kinetic resistance. That means diffusion resistance, right? So we kind of like have to see what kind of things we wanted, right? So when you kind of like prepare the sample, you also need to see what kind of like, when it kind of like enters into the system, what is the diffusion paths. It's a diffusion path is a straight one, not is kind of like a zigzag path, and so on and so forth. So we also need to see all these things when we prepare the sample. So which is a very important one, right? The second one is the activation. So activation means that when you prepare the sample, you don't know what kind of like gases are present inside. So this activation is to remove all the gases which present inside. So that's what we kind of like either do one of this. In the vacuum we will heat it, or we kind of like send the gas through it and heat it. And it's kind of like dependent on sample to sample. We don't follow the same technique all the time. So it depends on the sample, on the material, on the sizes, and so on and so forth. Once the activation is done, we do the breakthrough analysis. That means we let the gases enters into the system, right? And then we kind of like try to monitor the gas concentration at the outlet. Okay, this is the anyhow. So then we kind of like try to see with respect to the time, the concentration, right? So as we said, initially when we start the process, so all the gases will absorb into the system. Therefore, the initial concentration will be close to zero at all the time. So this part is called where the complete absorption is happening. So this is like here where we have unsaturated bed. So this is complete absorption part. In the second stage, what happens is that once the gas breakthroughs, right, at the breakthrough time, it goes through the breakthrough, and after that we reach a stage called saturation. So where whatever gas we send, it will come out. So these are the three stages. One is complete adsorption. So adsorbent completely absorb all the gas molecules. Therefore, we don't see anything at the end. Second one is breakthrough. So adsorbate gas is first detected at the outlet, and gas continues to absorb in the adsorbent. However, it's no longer able to absorb the entire gas. It may be partially absorbing something and partially releasing something. So that is the breakthrough region. And the saturation region, whatever gas you send in is coming out because it's already saturated. So whatever gas goes in comes out. Right. So how we do this one is that we kind of like calculate the amount it absorbed with respect to the time. So that is Ci is the initial, Ci is the concentration at any time t, which is final time. C naught is the initial concentration. Vi is the flow rate, and dt is the time. Okay. So what you see here is that in general we don't kind of like use the dead time and the final time. We kind of like go from 0 to t. But whenever we kind of like doing it in an experiment, we use the dead time. So the dead time is nothing but, say for example, you kind of like sending the gases from here, and then it has to flow through all these pipes and then come and then go to the final stage. So it requires some time. It is nothing to do with the absorption. It has to flow through all the pipes and the regions inside. So it takes some time. So we kind of like have to avoid that one. So for that one, what we usually do is that we kind of like perform. So this dead time is nothing to do with the gas or anything. It is only to do with the flow rate. So what we usually do, say for example, we are running this experiment at a given flow rate. That means Vi, we know the Vi. What we do is that we kind of like start an experiment something like this. So we have T versus Ci minus C naught, right? First, initially we kind of like send a tracer gas which does not absorb into the system. So then what happens? So the tracer gas kind of like goes like this. It's maybe a sharp curve you will see here because there is no absorption at all. So this first we perform on a tracer gas, right? This. So then we kind of like replace the tracer gas with the gas we wanted, and then see. something like that, right? So the area under the curve, which is in between these two things, will give you the amount adsorbed. Okay, that's how we calculate the amount adsorbed. Okay. Yeah. So this is tracer gas which does not absorb into the system. Most helium, hydrogen still absorb little bit, but most likely helium is the best one. It will not at all absorb. No other gas will be detected. It will detect the helium. So we will start with only helium first, right? So we will not perform these two things at the same time. Yeah, first we will do with the helium. Right.
How are we measuring that C by of the tracer gas? Because there is no other gas.
Right. So that's why when we kind of like go to the breakthrough time, that's the equivalent to the dead time, it sharply increases from 0 to 1. That's what you see here. Unlike here, which is actually going through a phase like this, when we kind of like run with a tracer gas, what happens is that, so this time is not the nothing to do with the saturation. This time is the dead time. That means the time required for a gas to flow from inlet to the outlet. Once it reaches the outlet, what happens is that the concentration sharply increases from 0 to 1 at the outlet. Yeah. Yes. Inlet pure tracer gas, right?
Then how can we measure from 0 to 1? Because the detector will give only 1. Because the concentration, there is no other gas.
No other gas, right?
Right. So it will always be 1.
Yeah, but to reach 1, how much time it will take? That's what we are interested in.
Okay.
Yeah. Okay. So this is how we kind of like a breakthrough curve looks like. So this is the region where you see complete adsorption, right? And then a breakthrough and then saturation. So the time here you see TB is the breakthrough time. So you may say like, why not here? Why here? Is that is where exactly we have to do is not in our hands. It's actually a limitation from the experimental side. So how much gas it can detect. So we may not able to detect when the like maybe in a very low concentration. So maybe at least it should have a little bit. So maybe like around 5% which we consider. So that time only we like our mission will able to predict it properly. So that's why like this is the TB, which is called breakthrough time. And once we reaches almost 100% saturation, even here also we kind of like say go with 95%. So that's called dead time, right? So the difference between TD minus TB is called the mass transfer zone. So which you kind of like have to have the information to understand the analysis of breakthrough curves. Okay. So any questions on this one? This breakthrough curves will tell you like how much gas it can absorb onto the system, right? So this is the information which we will get, which will be useful in designing the adsorption systems. So what our adsorption isotherms or kinetics we have, that will be helpful in screening the materials, but this will be helpful in kind of like understanding at a given flow rate how much it can absorb and at what time it needs to be regenerated.
For breakthrough, 100% of the gas is being absorbed. No gas is sitting in the port without being absorbed. That's super perfect.
So it may not happen. I'm like, so that I understand, but it depends on the packing and all. So how good the packing it is and all. So that's all kind of like goes into the sample preparation. So as you said, like if you go for a bigger particles, obviously the diffusion can happen between the particles. So then it may not be like perfect mass transfer situation, but we assume like in an ideal case it will happen something like this. Yes. Mhm. Yes. It won't be the same. Yeah, yeah. TD is the dead time is only not like TD is only to do with the gas of our interest, right? So whenever we kind of like see here, especially when we go for the tracer gas, right? So the breakthrough time and the dead time is exactly same because it will not absorb anything. It is only just time to pass through. Yeah. Yeah. Right. Yeah. And yeah, that's all. Okay. So then we kind of like go through a batch absorption process. So the like usually batch absorption process is often used when we have like small amounts to be absorbed, right? What we kind of like do is that, like especially for liquid solutions and so on and so forth, kind of like have a solution, then put a adsorbent into here, right? So then try to analyze the mass transfer here. Okay, so what we will do is that like we kind of like put a solution and an adsorbent here and try to measure the concentration in the solution with respect to the time. So the remaining solution is adsorbed into the solid. Okay, so yeah, so this is a simple mass balance equation which you see that the initial feed concentration is CF. That means whatever you have here is initially CF, right? And the final equilibrium concentration is C. That means after everything happened, the adsorption process is happened after time T. So the final concentration is C. So the difference will go into the solid. So that's what like you can see that the amount adsorbed will be calculated using a simple material balance like that. Okay. Anything else? Nothing interesting? Yes. MFCS, yeah. Okay. So then we kind of like look into the adsorption kinetics when a batch process something like this happens. So right. So as we kind of like discussed, one of the most important parameter is the rate of adsorption, rate at which the adsorption occurs. So therefore adsorption kinetics helps in determining not only the interaction between adsorbate and adsorbent, and also we kind of like get the optimum adsorption capacity and then potential rate limiting steps and so on and so forth. So governed by the surface complexity of the adsorbent, solute concentration and flow, the adsorption kinetics may be very different in all the situations. So some kinetics may foretells the adsorbate-adsorbent interactions. So based on the kinetics, we can say that, okay, it's kind of like a physical adsorption is happening, chemical adsorption is happening, and so on and so forth. So we kind of like also say the interaction between them. All right. I think we can skip this one, but so the only point here is that we kind of like talk about the adsorption kinetics now, like the curve. What we try to monitor is the concentration with respect to the time and try to fit the data. So whatever we have here is the concentration, sorry, the time here, the concentration here, then try to monitor how it goes or how it goes. It depends what you measure. So where you measure, that means that whether you are measuring in the adsorbate or in the adsorbent or in the solution. So and try to fit the data there. Right. So usually what we do is that we kind of like in batch process, what we do is that we measure the concentration with respect to the time and try to fit with one of these models and try to understand what is happening. So these are all the models. So it's kind of like only purely based on assumptions that we kind of like see that. Just want to go one by one quickly. So the first one is the pseudo first order model. It describes the adsorption kinetics by assuming the rate of adsorption is directly proportional to the difference between the equilibrium and current adsorption capacity. It does not consider any mechanisms like surface interactions or diffusion process or anything. It only says that as long as there is a concentration gradient, the gas molecules or any molecules will adsorb into the system. So this one pseudo first order typically used for the liquid phase adsorption systems, because whenever we deal with the gases, we should kind of like have to consider the diffusion. So usually when we kind of like deal with the liquid phase systems, we go with the pseudo first order. So as I said, here the kinetics, rate of adsorption is directly proportional to the difference between equilibrium and current adsorption capacity. So the equation we will write something like this. Qt, which is the adsorption at time t, is actually proportional to QE minus QT. So QE is the equilibrium one, that means the final it can achieve, and QT is the current one. So the difference in the concentration gradient is the driving force, and K1 is the rate constant. If you just integrate it in the limits of from 0 to t, so when time t is equivalent to 0, Qt is equivalent to 0, right? That means initially there is no solute present in the solid, and at time t, at any time t, Qt will be there. So you just model it, you just get an equation like that. Right, so that's the one first. So when we got the kinetic data, right? So when we have the kinetic data, we can use this equation and try to fit it. If we are able to fit with this linear equation, so that we say that it follows pseudo first order model. So that means that mostly concentration gradient is the one which is kind of like the cause for the adsorption, or like mostly rate limiting thing. Okay, so the second one is pseudo second order. Even this also can be kind of like mostly used for the liquid, to model the liquid systems. So it describes the adsorption kinetics by assuming the rate of adsorption is directly proportional to available sites in the adsorbent. So the first one talks about the difference in the concentration, but this one talks about the available sites in the adsorbent. Okay, so here the governing equation is dq over dt is equivalent to K2, which is another rate constant, is and times QE minus QT whole square. Okay. So the pseudo second order model may be affected by pH, the amount of dosage, particle size, temperature, and so on and so forth. So this model assesses the impact of observable rate parameters. So only one important thing here is that, so again, like same thing, you take the same boundary conditions. At time t is equivalent to 0, Qt is equivalent to 0, and then there are several forms available. This is one of the form which I have mentioned here. So it looks like what you see in Langmuir type of adsorption isotope. So you kind of like, yeah, fit into a graph t times Qt versus t, you will get a linear equation. If that is the case, then it follows a pseudo second order model. So what people kind of like believe is that whenever they observe kinetics with the pseudo second order model, they assume that it is something to do with the chemical adsorption, because whenever there is a chemical adsorption, they observe this is the case. So but please note that whenever you observe pseudo second order model, it does not mean that chemical adsorption is happening. If chemical adsorption is happening, you can able to fit the data with pseudo second order model. But whenever you are able to fit with pseudo second order model, it does not mean that chemical adsorption is happening. So the other way around is not correct. Okay. So what you have to do to verify it, you can go, yeah, so this is the one. So yeah, like say. So then what we kind of like have to do is we kind of like try to fit with L06 model, right? So this kind of like developed to especially to take care of chemi sorption. So it kind of like predicts the mass and surface diffusion, activation and deactivation energy of a system. So initially it kind of like proposed for a gaseous system, but it has been applied to many liquid systems as well. So this model assumes that rate of adsorption exponentially decreases with amount of adsorbed solute. So it looks something like this. dq over dt is equivalent to alpha times exponential minus beta qt. Alpha and beta are rate constants. So alpha is called initial adsorption rate. That is because when qt is equivalent to 0, that exponential becomes 1. So that dqt will be alpha, that is initial adsorption rate, and beta is the desorption rate. So it kind of like considers both adsorption rate and desorption rate and kind of like takes care of everything. So integrating in the limit of, again at time t is equivalent to 0, qt is equivalent to 0. So it can be linearized as this form. So you can kind of like plot qt versus logarithm of t. You will get all the parameters you wanted. So from the slope you will get 1 over beta. From the intercept you will get 1 over beta times logarithm of alpha beta. So this is kind of like applicable to both gaseous and liquid systems. So one we are very much interested in is interparticle diffusion model, right? So this is the model usually used to describe the diffusion controlled adsorption process. So whenever we kind of like deal with gas adsorption in a solid material, it is controlled by diffusion. So this intraparticle diffusion model is most likely be used to fit gas adsorption data in a gaseous system. Okay. So this kind of like considers the adsorption of a solute in the solution has to go through all these diffusion things. One is the film diffusion, 2 is the surface diffusion, 3 is the pore diffusion, right? As we discussed, what happens is that whenever you have a solid particle like this, right, and then you have a pore like this, right? So whenever we kind of like try to perform an adsorption, then what happens is that some gas molecules will adsorb onto the surface. So that's maybe near the surface. So it forms a stagnant film like thing here, somewhere here, because of the interaction between the solid and the gas. Okay. So whatever gas molecules that enters, right, it may be coming from here, it may be coming from here, it does not matter. It has to flow through this film kind of thing. So this film is happening because of the solid gas interactions. So it has to kind of like flow through the film of liquid or gas to enter into the system. So this is called film diffusion. So this model will take care of the film diffusion. The second one is the surface diffusion, which we kind of said, not all the gas molecules will enter directly like this. It may have to kind of like go through this. So that surface diffusion it has to take care. And the last one is the pore diffusion. That's like what is happening inside. So this model will take care of all three. One is film diffusion, second is the surface diffusion, third is the pore diffusion. Okay. So this model particularly useful in analyzing mechanisms of adsorption in porous materials, which is of our interest, like activated carbons, zeolites, MOFs, or whatever. So it kind of like follows something like this. So QT is the adsorption capacity at any given time is equivalent to Kp, which is the rate constant, times square root of T, that is the time, and C. So this is a very easy model. What you kind of like has to do is just need to fit square root of time with Qt. That's it. So it should be a straight line with a slope of Kp, then the constant. Intercept will give you a constant C. Everything else will be taken care of. Okay. Yeah. So any questions on breakthrough on the models? Yes. With diffusion coefficient? Yes, it will be, because it kind of like takes care of all the diffusions. But what diffusion coefficient we need to see, whether we are talking about the most likely the D, which is like, say, although we kind of like say in terms of resistance I will talk. So we said like there will be three types of resistances. One is like going through the film kind of thing, and then the surface, and then inside. So the resistance which we get, like this intra resistance, is pretty high compared to these two things. So most likely the diffusion inside is the limiting step. So this D is kind of like related to Kp, because these two things are most of the times negligible. So this D is kind of like related to Kp. Right. Any questions? Any online questions? Srid? Yeah.
So we have some time left. If you want, we could go through the topic again. Is everything clear?
Okay, that's good. They have, okay, so all good. So thank you so much. If you got any questions, please feel free to write to me. You have my email ID somewhere there.